Isoperimatric inequality for flat surfaces. Okay. Let me first start with a domain D in R2. And let A be the area of D and L the boundary length of D. Then it is well known that 4 pi A is less than or equal to L squared, and equality holds if and only if D is a disk. And people have been trying to generalize this inequality in many directions, and one of them is generalization into flat surfaces. Flat surfaces are surfaces with flat metric. And the plane has zero Gaussian curvature. Similarly, flat surfaces have the zero Gaussian curvature. And another generalization is into minimal surfaces. You can call minimal surfaces generalized planes. Because minimal surfaces are locally area minimizing, and because mean curvature of the minimal surface vanishes, just like a plane. Okay? And one cannot always generalize the isoperimatric inequality on the flat surfaces. There's a counterexample, which is a long cylinder. If this cylinder is very long, then the area A can be very large, whereas the boundary length, which is the union of two circles, is fixed. So this does not hold on this long cylinder. So we cannot have 4 pi A less than or equal to L squared on this cylinder. As for the minimal surfaces, boundary is not connected.
It's connected.
Oh, you mean if the boundary is, if there's only one boundary? Yeah, then, yeah, it's true, yeah. And for the minimal surfaces, it was conjectured that the same isoperimatric inequality should hold, which is the same as this one. Okay? But this conjecture is still open. This was proposed about 90 years ago, and the first result, partial result, was obtained by Kaliman in about 1920s. He proved that this sharp isoperimatric inequality holds for a simply connected minimal surface in Rn. Okay. And then there are many partial results, and the most recent one was obtained by Li, Shane, and Yao, and also by myself. And these two results together imply that the isoperimatric inequality holds if the number of boundary components is equal to 1 or 2. Okay, so today I'm going to talk about three theorems. One Isoperimatric inequality in Euclidean plane, and one theorem in flat surfaces, and one theorem for the minimal surfaces. Okay. So the first Isoperimatric inequality is for the plane. I'll introduce you the theorem by Gromov. This proof is very interesting, and this proof uses area minimizing map. Given a domain D, he constructed a area preserving map. Area preserving map. And here is a domain disk B, which has the same area as D. So area of D is equal to the area of B. And he constructed this map psi, which preserves area. And this map psi also maps the vertical line onto a vertical line on B in such a way that this part of the left part has the same area as the left part of this vertical line. Okay? So if this point with coordinate AB is mapped onto CD here, okay, here you have XY coordinate system, and here we have UV coordinate system. Then the assumption is this: area of the set for x less than A is equal to area of the set U less than C. Okay? And furthermore, here you have infinitesimal strip, and this part has the same infinitesimal area as this infinitesimal strip. Okay? In other words, the length of x equal to A and y less than B times infinitesimal width dA equals the length U equal to C and V less than D times dC. Okay. So by these assumptions we can show easily that this map psi preserves area. Okay? So let's let d psi be the Jacobian of psi. Then d psi equals du dx, du dy, and dv dx, dv dy. But this map psi maps a vertical line onto the vertical line. And on this vertical line, x is fixed and y varies. And on this vertical line, u is fixed and v varies. So as we move in this direction, u is fixed. So dy du vanishes. Sorry, du dy. This vanishes. Okay. So we have lower triangular matrix. Okay. Then the determinant of the Jacobian preserves area, so its determinant equals 1. So its square root times 2 equals 2. This is not power, but 2 times. Okay? And this Jacobian equals t du dx times dv dy. Which is by Cauchy-Schwarz du dx plus dv dy. Okay, so now let's introduce vector field. I'm going to introduce a vector field on this domain D. Vector v at P is defined to be the position vector of psi P. So this point is mapped onto this point. The origin is here, so this is the position vector. So here we assign vector v pointing in this direction. Okay.
du dx and dv dy are positive.
Du dx dv dy. Yeah, we have to du dx. Du. Yeah, we are increasing. The vertical lines going in this direction are mapped onto the vertical lines going in the same direction, so they are all positive. Yeah. Yeah, we are always going up. Okay. Yeah. So in this way, we can introduce the position vector field V. Okay. Then this is nothing but the divergence of position vector field V. So we have this inequality 2 less than or equal to divergence of V. Then let's apply the Stokes theorem. 2 times area of D is less than or equal to the integral over D of the divergence of V. By the Stokes, this is equal to integral over the boundary of V dot n, eta, where eta is unit normal, outward unit normal. To the boundary of D. And this boundary integral is less than less than what? Okay, before that, let's consider the following. The area preserving map psi maps the boundary of D only onto the boundary of B. Okay. And on the boundary of B, the vector, position vector has the same length, which is the radius of the disk. What is the radius of this disk? Radius r squared times pi equals the area of B, which is equal to the area of D. So r equals a over pi and its square root. Therefore, on this boundary of D, the length of V is always equal to that. Yes. So this quantity is less than or equal to the length of V, which is square root of A over pi times the length of eta, which is 1, times the length of the boundary, which is L. Then combining this left-hand side, which is 2A, with the upper bound, which is this, we obtain the desired inequality. 4 pi A is less than or equal to L squared.
Where did you get the less inequality? Smaller than
this is less than or equal to boundary of D, integral over boundary of D of length of V times length of eta, which is 1. Okay? And length of V on this boundary is always equal to this. Length of V on this boundary points are mapped onto this boundary. So on this boundary, V always has the same length, the radius of the disk, which is this, the radius. Yeah. And when equality holds here, we have to have equality here, and you have to have equality here. When you have equality here, you need to have equality here. So these two have to be identical, which is equal to 1. So this is equal to 1, and this is equal to 1. And then by this equality, it's not difficult to show that the equality holds only when D is a disk itself. Okay. So that's a beautiful proof given by Gromov. And I tried to generalize this proof to prove this conjecture, but I failed. Instead, I only proved the relative isoperimatric inequality for domains in Euclidean space, applying the Gromov's technique. Okay, so that's for the Euclidean plane. And
it's easy to find psi.
Psi, the area preserving map. Yeah, you can. So once you have this area is equal to this area, then this point is mapped into this, and this point is mapped into this. You just go up linearly, okay? And this point is mapped into this point. In this way, you can, in a way, topological definition or affine definition of the map. Okay. It's quite interesting, but mathematician Moser proved that given any two domains with the same area or volume, you can always find the area minimizing map. Sorry, area preserving map. He proved that in general. But in Gromov's map, psi not only has this property, but also has this vertical point preserving property, a vertical line. Vertical lines are always mapped onto vertical lines. So
only one vertical line?
All the vertical lines here. Yeah. Even all these vertical lines are mapped onto the vertical lines. This can be generalized to higher dimension, even in R3. Given a three-dimensional domain, you can all similarly construct volume-preserving map. Okay.
So what is I sport? What is I sport?
right?
The right-hand side is pole. Against the sphere and this, right?
Yeah, this one is sphere, ball, three-dimensional ball. Yeah, higher dimension, yeah. So this holds in higher dimension, even in Rn. This proof works for Rn as well. Okay, so that's Euclidean case. And let's consider flat surfaces. Okay, so that was Gromov's theorem, and from now on, this is a joint work with Rueckschein. And we proved the following theorem. F is a flat surface and if the rays emanating from each boundary point of F never intersects each other, then 4 pi a is less than or equal to L squared. And also equality holds if and only if F is a disk. We have a strange hypothesis that okay, let me give you an example. Let's identify this part of boundary with this part. Okay. Then you get a flat surface whose boundary is inner circle and outer circle. Okay. Choose any boundary point and consider any ray emanating from that point. Any two rays emanating from the same point do not intersect each other. Okay? If that is satisfied, then this Isoperimatric inequality holds. On this flat surface, this hypothesis holds, but if you consider here, from this boundary point, if you identify this boundary with this boundary, if you go in this direction, then this point is identified with this, and then it goes back. Okay? And then from this same point, you can consider this ray, and these two rays intersect each other here. Okay? So this flat surface doesn't satisfy this hypothesis. So we cannot obtain this Isoperimatric inequality, and indeed this doesn't hold for this flat surface. Okay? So we have this Isoperimatric inequality only for this. So 4 pi a is less than L squared, but for here, for this, we do not have this inequality. Okay? Similarly, if you have a cylinder is like this. Top part is identified with this bottom part. Then consider this ray, which becomes this ray, but this ray intersects another ray from the same point. Okay, so we have this intersection. So this hypothesis is not satisfied on this cylinder. Okay? Our proof is based on the integral geometry. Given a domain D, the area is equal to double integral of 1 over D. Okay, then let's to each point, let's associate infinitesimal rays, line segments emanating from this point. Okay, and here we can also consider infinitesimal line segments. And here we have line segments like this. So at each point we associate these infinitesimal line segments which rotate by 360 degrees. Okay, so the total mass of the infinitesimal line segments on D should be 2 pi times area. Okay. And then we have these line segments at every point inside the domain D. Okay. Then these infinitesimal line segments together form lines. For example, consider these line segments, infinitesimal line segments. They form a line segment inside D. And these infinitesimal line segments form a line. Okay. So this total mass of infinitesimal line segments is equal to the total mass of the line segments inside D. Okay. Then let's parameterize this set of line segments. The set of all line segments in D can be parameterized by two variables, S and theta. Okay.
What do you mean line segment?
This line segment and this line segment.
Infinitesimal line segment, right?
Inside D, yeah.
So that meaning for each point there is
Yeah. At each point you have actually infinitely many line segments like this.
what do you mean by integration?
Yeah, I'm cheating a little bit, but intuitively I'm telling you this explanation. Just
Also integrated
Yeah.
unit circle.
yeah, at each point. At each point, yeah. Okay. That's how we got this 2 pi. Okay. So we try to parameterize the set of all line segments with two variables, S and theta. S is the arc length parameter of this boundary of D. So on this boundary we have arc length parameter S. So for this line segment which intersects the boundary point here, and for this boundary point we have specific value of the arc length S. Okay. And also we have angle theta, which is exactly this angle. So you have S from this point and you have this angle. Okay. So the total mass of line segments is actually total integral of the length of the line, each line segment, times d theta against d theta and ds. But here we need to make some adjustment. Okay? all line segments are not equal. Okay? In other words, let's consider choose this point and emanate line segment like this, okay, to the boundary. Then the power of this light ray over the boundary depends on this angle. If this angle is 90 degrees, then its power is the biggest. If this angle is very small, 0, then its power vanishes. Okay, so we have to take that into account, the power of the light ray. So that adjustment can be made by the power, which is exactly sine theta. So sine theta. We have to multiply by sine theta here. And the length L depends on two variables, s and theta. Okay? And theta varies from 0 to pi, and L varies from 0 to L, the boundary length of the domain D. Okay? And now we use Hölder inequality. By Hölder, this is less than this is easy. And the integral of sine squared, we can compute this. Any high school students can compute this, which is pi over 2. So this factor becomes pi over 2 times integral of this constant over this interval L, so 2 pi square root. Okay, and this is not simple. Okay, for this integral, we have to fix the boundary point. Fix boundary point here, and integrate L squared. And by the polar coordinate, we know that the integral of L squared, what is it? Over all rays emanating from this fixed point. This area element is 1/2 L squared d theta, right? So integral of L squared d theta gives us 2 times area of the domain here, right? But things are not that simple for non-convex domain. If you choose point here, then all rays emanating from that comes up to here. And then, so this part is not covered. Okay? So we only have this inequality. That's still okay. But the case we cannot accept is this. Fix this boundary point and consider all the rays emanating from that. It looks good, but not exactly. We have to identify this boundary with this boundary. Therefore, this ray continues in this way, and this ray goes in this way, and this ray goes in this way. So these rays overlap each other at least twice. Okay?
Ray is geometry.
Yeah, just a line segment emanating from one fixed point.
Flat surface always
Yeah.
there's some part of plane.
Yeah, exactly. Yeah. So in this case, we get the bad direction of the inequality. So we don't want that. That's why we introduced this hypothesis. With this hypothesis, this overlapping doesn't happen. So we always have this inequality. Okay? So integral of this upper bound, which is a constant 2a over this interval, it becomes 2al square root. So combining this left-hand side with this right-hand side, we get the desired inequality, the Isoperimatric inequality. Okay. Okay, finally, the minimal surfaces. Okay, let me briefly present you minimal surface theory, which leads to the Weierstrass representation formula. Okay? So given a submanifold in R3, sigma 2, we use coordinates, rectangular coordinates, Euclidean rectangular coordinates x1, x2, x3. Then we can define an immersion psi, which is x1, x2, x3. Then the Laplacian of the immersion, this vector valued function over the intrinsic metric of sigma is equal to the Laplacian over sigma of x1, Laplacian of x2, Laplacian of x3, and this is known to be the mean curvature vector of the submanifold sigma. Okay? So if sigma is minimal, then mean curvature vector vanishes. Therefore, rectangular Euclidean coordinates are all harmonic on the minimal submanifold, minimal surface. Okay? Now let's introduce complex coordinate z, x plus iy. On sigma. Then x and y are isothermal coordinates on sigma. And the metric is 2 lambda times dz length squared. So 2 lambda is the conformal factor. Then, since x1, x2, x3 are harmonic, we can differentiate with respect to complex coordinate z. So, and these derivatives are all harmonic, all holomorphic. So let's call it phi1, phi2, phi3, and these are holomorphic. And the map psi, which maps x, point x, y to x1, x2, x3, is conformal. Therefore, phi1 squared plus phi2 squared plus phi3 squared equals the length of vector psi x squared minus psi y squared minus 2I psi x dotted with psi y. And since psi is conformal, this equals that, and this vanishes. Therefore, the sum equals 0. Okay. Now let's introduce holomorphic function f, phi1 minus I phi2, and meromorphic function g, which is phi3 divided by phi1 minus I phi2. Then, from this equation, we can solve for phi1, phi2, phi3 in terms of f and g. Therefore, x1, x2, x3 equals the real part of 1/2 integral f 1 minus g squared dz, and I over 2 integral f 1 plus g squared dz, and integral f g dz. This is the Weierstrass representation formula. All the minimal surfaces in R3 can be obtained from this formula. Yeah?
The Chi1, Chi2 is the real length, right?
Phi, this one?
Origin, yeah.
Psi.
Chi1, Chi2, real length.
X1, X2, X3, yeah, real. Ambient space coordinate.
Why is the holomorphic Chi1?
They are harmonic. From this, X1, X2, X3 are harmonic. If you differentiate the harmonic function with the complex coordinate z, you get the holomorphic function. Yeah. Yeah, what is this? 1f dx1 dx minus dx1 dy, right? In this way, you can differentiate real function. Yeah. Okay. Then the conformal factor 2 lambda and 4 lambda equals actually the length of phi1 squared plus phi2 squared plus phi3 squared, which is, in terms of f and g, the length of f times 1 plus the length of g squared over 2. Okay. And the Gaussian curvature of the minimal surface is minus 1/2 Laplacian log lambda, which turns out to be negative or non-positive. Right? And now the key idea is the following. Here, Laplacian of log lambda turns out to be negative. But sometimes we can make that 0. Okay? And not exactly that, but something as follows. Let's, okay, let me write here. Let's introduce new metric, G1, which is 1 over 4, the length of f squared, dz length squared. And G2, 1 over 2, fg squared, dz squared. And G3, 1 over 4, fg squared, dz squared. Okay. Then, for this metric, 2 lambda dz squared, for this metric, Gaussian curvature is negative. But for these metrics, Gaussian curvature is what? Minus 1/2 Laplacian log holomorphic function squared. You know, these absolute values are the absolute values of holomorphic functions. So their log is harmonic. So its Laplacian vanishes, right? So for these three metrics, the Gaussian curvatures are all zero, okay? Unlike this metric, okay? So on this minimal surface, the Gaussian curvature is negative, but from the minimal surface, we can extract three flat metrics for which Gaussian curvature vanishes, right? Yeah?
이게 the second line.
Yeah.
So psi x, y, inner
Yeah.
part, right?
Yeah.
Inner part is the real number, right?
Yeah.
But the left side is real number, but this y is 2i. 2i minus 2i.
Yeah, it takes a long time. Why don't you compute this? Yeah.
But everything is real number, right?
Yeah, but this is holomorphic function.
But
This is a holomorphic function.
real number.
No, holomorphic. Yeah. So for any of these, the metrics are, the Gaussian curvatures are zero. Okay, so we have three flat surfaces arising from one minimal surface, F1, which is minimal surface, not with the original metric, but the first flat metric G1, and F2 with second flat metric, and F3 third flat metric. So out of original minimal surface sigma, we obtained three flat surfaces. Okay. The idea is to use these flat metrics to prove the Isoperimatric inequality of the original minimal surface. Okay. And how do you do that? We are using the following key theorem. If F1 and F2 satisfy the standard Isoperimatric inequality, then so does sigma. Okay? So the proof of the Isoperimatric inequality for minimal surface is reduced to that of the Isoperimatric inequality for the flat surfaces, F1 and F3. So we don't have to worry about this flat surface. We need only these two flat surfaces. Okay? And why is that? Okay, let me give a short proof. Let A be the area of minimal surface, original minimal surface, and AI be the area of flat surface Fi, and the length of the boundary of minimal surface, and Li, the length of the boundary of flat surface Fi. Then the area of the original minimal surface is by definition integral over 4 the length of f squared 1 plus g squared dx dy squared. Then let's expand this square, okay? And we can expand it into three integrals. The first is 1 over 4 f squared. The second is 1/2 f g squared. The third is integral over 1 over 4 f g squared. Okay. Then this is exactly equal to a1 plus a2 plus a3. How about L then? L is equal to integral over 1/2 of the length of f, 1 plus the length of g squared ds. This function is the square root of this function, okay? Because this is area, the length. Okay? Again, let's expand this integrand. And this becomes then 1/2 the length of f plus integral 1/2 f g squared. Okay? And this As by this definition, exactly L1 plus L3. But note here, we don't have L2 here. We have no L2 here, while we had A2 here. Okay, so since we don't have L2 here, let's get rid of A2 here. So how do we eliminate A2? A2 squared equals 1/2 FG squared. Here again, by Hölder inequality, we have a product of two integrals. 1/2 F squared times 1/2 FG squared. Okay? Which is exactly 4A1, A3. So we can express A3 in terms, we can express A2 in terms of A1 and A3. That way we can eliminate A2. Okay? So now finally we have the following. Let's start from the left-hand side of the Isoperimatric inequality. Then 4 pi times area is equal to 4 pi times A1 plus 4 pi times A2 plus 4 pi times A3. Then let's get rid of A2. So this is less than or equal to 4 pi A1 plus 8 pi square root of A1, A3. We used this inequality, okay? Plus 4 pi A3. So we don't have A2 anymore. Then let's use our hypothesis. F1 and F3 are assumed to satisfy this inequality. So A1 is 4 pi A1 is less than L1 squared. So this is less than L1 squared. And 4 pi A3 is less than L3 squared. And A1, A3, 4 pi A1 is less than L1 squared. And 4 pi A3 is less than L3 squared. Which is exactly L1 plus L3 squared, which is equal to L squared. So finally we get the desired isoperimetric inequality. Okay? Okay. So this is the final theorem for the minimal surface. Theorem 3. If sigma is a minimal surface, with all fluxes parallel to a line, then sigma satisfies 4 pi A less than or equal to L squared. Okay. Okay. Let me briefly introduce the notion of flux. Flux of a minimal surface sigma along a component, boundary component of component gamma 1 of the boundary of sigma. Okay. Here we have minimal surface with two boundary components, and here we have normal vector nu. Nu is unit, and nu is normal to the boundary of minimal surface. And finally, nu is tangent to the tangent plane of the minimal surface. So nu is a tangent vector, but that's normal to the boundary of minimal surface, and nu has unit length. Such a vector nu is called unit conormal. Then the total integral over the boundary component gamma 1 of nu is called the flux. This flux. Okay. Okay, but what is nu? What is nu? Nu is actually nu of x1 and nu of x2 and nu of x3. Let's consider unit tangent vector tau, tangent to the boundary. Okay? Then nu equals complex structure J of tau. In other words, nu can be obtained by rotating tau by 90 degrees. Okay? Therefore, by Cauchy-Riemann equations, this is equal to tau of x1 star, which is the complex, which is harmonic conjugate of x1. And this is nu of x2 equals tau of x2 conjugate, tau of x3 conjugate. This is just by Cauchy-Riemann equation. So, by this observation, this total integral, the flux, which is the total integral of the unit conormal, is nothing but the period of the conjugate surface, sigma star, along gamma 1. The integral of tangential component of x stars, x1 star, x2, x star, x3 star, which give us the conjugate surface of the minimal surface. Okay? Therefore, this is nothing but I erased the Weierstrass representation formula, but this integral, the period, is exactly the imaginary part of Weierstrass representation. Okay? Okay, now let's introduce a new coordinate such that x1, this is x1, x2 plane, which is normal to the flux. This, we have flux along this boundary component gamma 1 and along this boundary component gamma 2. By this hypothesis, all the fluxes are parallel to one line. Okay? So we take x1, x2 plane to be orthogonal to this flux line. Okay? Then, by this positioning of the x1, x2 plane, this imaginary part becomes 0, 0, and some constant c. Okay? But from the original Weierstrass representation formula, the real part of the same integral also vanishes. All three integrals, real part vanishes. Therefore, we know that for these complex integrals, the imaginary part along the boundary component vanishes, and also real part vanishes. So this complex integral is well defined, because along the boundary, both real part and imaginary part vanish. So finally, we can conclude that therefore, integral over the minimal surface of this complex integral and integral over these two complex integrals are well defined on the minimal surface. Okay? So their linear combinations are also well defined. Therefore, integral over sigma of f dg and integral of f g squared dg are also well defined. But what's the image? What's the image of these complex integrals? The image, okay, this complex function is f1. So f1 maps minimal surface onto flat surface. But these are well defined. Well defined means that this image lies exactly in R2. It doesn't exist abstractly. It exists in R2 naively, very naively, as a domain on R2. Okay? Similarly, F3 exists in R2. So we have a well-known isoperimatric inequality for F1 and F2. On R2, we know that the isoperimatric inequality holds. So for these flat surfaces, we have the isoperimatric inequalities. So by the previous theorem, theorem 2, we know that F1, F2 satisfy, if F1, F2 satisfies perimetric inequalities, then the resulting minimal surface also satisfies the same isoperimetric inequality. And from this, we can obtain more corollaries, and we can also prove more complicated theorems. So that we improved a little bit. So far, we, as I said earlier, the result.
So from a minimal surface, you can construct three kind of surface.
Three flat surfaces, yeah.
But metric is definite.
Metric.
For each.
You mean you have to go up to the universal cover. You have to.
Because maybe it has zero.
Oh yeah, sure, yeah. It may have branch points. Yeah, yeah, right. It doesn't matter. Yeah, it doesn't matter. Okay.
Yeah. Thanks.